It's a great pleasure to welcome Nguyen from Iowa State, and she will speak on the strangling of the fundamental gap in the hyperbolic space.
So thank you, Alina, for inviting me to talk. So if you're looking for the article on arXiv, it's called The Vanishing of the Fundamental Gap in Hyperbolic Space. With so many authors, we had a bit of back and forth about what title to give it. And so you might hear various talks with different titles, all completely exotic, but it's the same idea. And as Alina said, the group met last June in Oaxaca, and we started on working on a couple of problems, and it's very productive and a lot of fun. I started writing a Beamer talk and then realized that none of you would be in the back of the room, so none of you really need giant fonts. So now it's going to be on the right side here, it's going to be the main talk. And on this side, since I have also control of both sides, it's going to be things that I want you to keep in mind or that I would need to refer for later. So let's see. Let's introduce what the fundamental gap is. We're mainly looking at bounded smooth domain in omega in n-dimensional manifolds, and looking at the eigenvalue equation of the Laplace on omega. So Laplacian phi equals minus lambda phi. With Dirichlet boundary conditions, so when phi is 0 on the boundary, we know that the first eigenvalue is simple. So lambda 1 is strictly less than lambda 2. And those are the only two I'm going to be interested in right now. There are many works about estimating the eigenvalues, especially lambda 1, and there's also a lot of work about Neumann eigenvalues. The basic tool we're going to use is the min-max principle. So the eigenvalue is characterized as the infimum over k-dimensional subspace, lambda k, over the supremum of all those functions in the subspace of this quotient. So for lambda 1 is just the infimum of the integral of the gradient square normalized. So we divide by the integral of phi square. And lambda 2, we take the functions that are perpendicular to phi 1, which is the first eigenfunction. The fundamental gap, so the gap between the first two eigenvalues of the Laplacian, or you can take more general Schrödinger operators, is called the fundamental gap. It's an important quantity in math and physics. So for example, in physics, it tells the amount of energy between the steady state, which is the first eigenstate, and the second one. All the problems are, find good estimate on the fundamental gap. What is optimal upper bounds? What are optimal lower bounds for the gap? So let's take an example, very simple. On an interval, 0D is one dimension, so Laplacian is just second derivative, and it's second derivative of phi plus lambda phi equals 0. When you solve it, you have a general solution, which is C1 sine square root of lambda t plus C2 cosine of square root lambda t. If we have Dirichlet boundary conditions, then the eigenfunctions are phi k is sine of k pi over d t for k greater or equal than 1. So k equals 1 is the first eigenfunction, and k equals 2 gives the second eigenfunction. If you take the derivative of this twice, you find that lambda k is k pi over d squared, and lambda 2 minus lambda 1 is 3 pi over d quantity square. Now, let's take the next dimension, and the simplest example is a rectangle, which is length L and height epsilon. Now, the Laplace phi plus lambda phi, that's also very standard. We can separate variable. So I'm going to write h of x, f of y. And you see that the first two is the Laplace operator plus lambda fh. Then I divide by fh and I get the second equation. Oops, let me go to this side. And so this is a function, the red part is a function of y exclusively. It's going to be equal to a constant, and the constant we've seen from the previous example, let's write it as minus k squared pi squared over epsilon squared. And the blue part is also a constant, which is the same constant. So hxx plus lambda h is k squared pi squared over epsilon squared times h. It's a little weird to write it this way, but you will see when I go to the hyperbolic case why I'm writing it this way. So lambda minus k squared pi squared over epsilon squared is L squared pi squared over L squared, where k and L are positive integers, or they can also be negative integers since we're taking a square. So now the question is, which one is the first one? Well, the first one is when k equals 1 and L equals 1. Which one is the second eigenvalue? Well, you can take k equals 2 and L equals 1, or k equals 1 and L equals 2, and compare. And the smallest one is going to be the second eigenvalue. So when L is greater than epsilon, as I said, this is the first eigenvalue, when k is 1 and L is 1, and this is the second one. So here we take L equals 2, and the fundamental gap, now is the difference of lambda 2 minus lambda 1 is 3 pi squared over L squared. L is not really the diameter. The diameter is the diagonal, which is almost L. It's going to be L. So when epsilon goes to 0, L goes to the diameter. And so the fundamental gap is going to go to 3 pi squared over d squared. So 3 pi squared over d squared seems to be an interesting quantity. Let's look first at convex domain on Rn and Sn. So for bounded convex domain in Rn and Schrödinger operator, so minus Laplace plus V, where V is now negative convex. And again, we're taking Dirichlet boundary condition. The fundamental gap conjecture in the 80s by these people says, hey, the fundamental gap is going to be greater or equal than 3 pi squared over d squared for every convex domain and every Schrödinger operator of that form. As we've seen before, we have an example where the lower bound is approached when v equals 0, and if you take thinner and thinner rectangle. So it is a sharp constant. Is it a sharp lower bound? Oops, not that side. So the progress in Rn started with Singer, Wang, Yao, Yao. They prove it's greater or equal than pi squared over 4d squared. And then pi squared over d squared. And some of these estimates use the fact that the first eigenfunction is log concave, so that the log of the first eigenfunction is concave. Then Levine proved this for one dimension, and it has a potential, of course. One dimension without potential, we just did. And finally, in 2011, Andrews and Clutterbuck proved the fundamental gap conjecture for convex domains in Rn. So it is true in Rn. Now, if you only take triangles, this is the estimate. So it's slightly higher, 64/9. What happened in Sn? So again, bounded convex domain in Sn, we have fundamental gap is greater or equal than pi square over d square. It's a result of Li Wang and Wang in 1987. And then with potential, it's 1993. Then various people, Wei is Guofeng Wei, which is one of the co-authors, have proved it in dimension greater or equal than 3 for diameter less than pi over 2, then greater or equal than 3 for diameter less than pi, and pi is the biggest diameter you can have in Sn. And then finally, for dimension 2, for the diameter less than pi. So it is also true in Sn that the fundamental gap is greater than 3 pi square over d square. I believe that in Sn, we don't have an example where the fundamental gap tends to 3 pi square over d square. It's possible that it's also a thin quote unquote rectangle, but the separation of variable is not really nice at all. And so it's still open to find a limiting case in Sn. Now, what happens on hyperbolic spaces Hn? When we were at that conference or workshop in Oaxaca, we read this article by Xi, 1989, and says there are convex domains such that the first eigenfunction is not log concave, which was something that happened in Rn, in Sn, and was an ingredient for proving some of the lesser inequality. The full conjecture was proved with other techniques. But log concavity does play a role in estimating the fundamental gap. The first eigenfunction is not even quasi-concave. So quasi-concave means that if you look at the sets where a function is greater or equal than a constant, then you get a convex set. Things we know about eigenfunction in hyperbolic space is an article of Ben-Gurion and Linde, 2007. It says if you have a bounded domain, it doesn't have to be convex, then the fundamental gap is less than the fundamental gap of the corresponding ball. And the ball corresponding means that the first eigenvalue of the ball has to be the same as the first eigenvalue of the domain. So in other words, they prove that the second eigenvalue of the ball is always greater than the second eigenvalue of the domain if the first ones are equal. So this was our first result. We found convex domain in H2 with very large diameters, actually, for which the fundamental gap is strictly less than 3 pi square over d square. So it seems like this is not a good lower bound. Well, it is not a good lower bound for hyperbolic space. But we did find that the fundamental gap of Xi's example is greater or equal than 3/2 pi square over d square. So now the question is there a lower bound? And if there is a lower bound, what is the lower bound for the fundamental gap in hyperbolic space? Then this summer, well, spring, it took a while to write, so it gets submitted this summer. We showed that there is actually no lower bound. So in dimension greater or equal than 2, for any epsilon positive, you can even pick the diameter positive fix. There exists a convex domain omega with diameter d such that the fundamental gap is less than epsilon pi square over d square. That means we can choose domains for which the fundamental gap tends to 0. So it's a big departure from what happened in Rn and Sn. So these are the domain. This inspired by Xi's domain, but they're not symmetric. So the angle on the left side is not quite the same as on the right side. So let's consider H2 with upper half plane model. So y strictly greater than 0, and put some polar coordinates. So r is positive and phi is between minus pi over 2 on this side and pi over 2 on this side. The metric is given by this, dx squared plus dy squared over y squared. And the domains, r is between 1, so s, t, and p are when r equals 1, and e to the pi over square root of mu. And mu is going to tend to infinity. So the domains would get thinner and thinner and thinner. And phi would be between minus L and L. So I move this here so you can keep a picture.
So your domain will be degenerating in some sense, like to a segment in a
Yes.
hyperbolic space, right? And so then the two eigenvalues somehow will approach an eigenvalue of a segment in some sense, right? Like in Gromov-Hausdorff.
Yes, but as you see, the eigenvalue of the segment in R is different than, so I will show that the two eigenvalues actually, lambda 2 will approach lambda 1 rather than eigenvalues of the segment.
Yeah, okay, thank you.
So the diameter of the domain, this is proof. So this is the same type of domain in our first article and the second one. And these computations are done in the first one. This essentially says that we prove that the diameter is the diagonal, sort of. So the distance from R to P, which is the same as the distance from S to Q. And so the left-hand side is the distance from P to S, which is kind of strange in this hyperbolic space. The distance PS is the same as the distance RQ. And so the distance PS is less than the diagonal, which is the diameter. And this one is PT TU UR. So this is a geodesic, UT is a geodesic, TP is a geodesic. What it also says is that for fixed L, there is a bound from below and above, independent really of mu, as we would let mu go to infinity. So the diameter is bounded. If we want to prove that something is less than epsilon pi square over d square, and we have a bound on the denominator, we just have to prove that we just have to prove that this goes to 0 and not really worried about the diameter. So let's separate variable. We separate variable, the Laplace u equals minus lambda u becomes this thing. And let me go back here a second. With both Dirichlet condition. So it was the same thing. If you separate variable, there's something in F that was a constant, and we call the constant k squared mu. There was something in H that was a constant, and we call it k squared mu. And let me go over here now. Wait. Nope, I think I'm missing a slide. Oh well. So if you solve this, you have that lambda 1 is when k equals 1, and you take the first eigenfunction, lambda of equation 2. Sort of the same as we did here. K equals 1, and we took the first eigenvalue, which was L equals 1. So whatever the first eigenvalue here is going to be the first eigenvalue. This is first eigenvalue given mu, and that's the first eigenvalue of the domain. If I want the second eigenvalue of the domain, it's a toss-up between increasing k equal 2, so that's lambda 1, first eigenfunction of the second equation with k equals 2, or taking k equals 1 and taking the second eigenfunction of equation 2. It's actually this one. It's actually the second, this one, which it's the same thing as in our rectangle in R2. It doesn't really matter. So we're not actually proving it has to be one or the other, because the second eigenvalue of the domain is less or equal than lambda 2 mu. So if we can show that lambda 2 mu minus lambda 1 mu goes to 0, then we have that the fundamental gap goes to 0. What this slide tells us is that I have to look at the first eigenfunction and the second eigenfunction of 2 when k equals 1. And if I can compare the first and second eigenfunction of the second equation, then I'll have a result on the fundamental gap of the domain. All right, so I'm saving this equation, which is the only one we're going to look at from now on. Note that you can choose the first eigenfunction to be positive. And because of the fact that the coefficients are symmetric with respect to phi, H1 is also going to be symmetric with respect to phi. So H1 is going to be even. So here's the plan. The plan is to show that the first eigenfunction, which is symmetric, behaves like this bump. We're going to show that the maxima, the two peaks, will move towards minus L and L, and that H1 of 0 would go towards 0 as mu goes to infinity. So as the strip domains get thinner. So this is far from being log concave. And in fact, since you have two maxima, there is no way that if I take a level set, so if I cut it off and see where H is bigger than a constant, then I have disconnected sets which are not convex. We have to make the first line precise. So the maxima will move to the outside and H1 will go to 0. And then once we have that, we'll use the Rayleigh quotient. So this is the Rayleigh quotient associated to this equation 2. And lambda 1 is the Rayleigh quotient of H1, and lambda 2, well, it's the Rayleigh quotient of H2, but we can estimate it by taking psi times H1. So psi is this odd function, and so the dotted line is an estimate of the second eigenfunction. And note that the dotted line is perpendicular to H1 because there's an odd and an even function. So the Rayleigh quotient of the dotted line is going to be greater or equal than lambda 2. And you also see why So if you take the Rayleigh quotient, everything happens in this tiny interval. So it's very important to know the behavior of h at 0, that it goes to 0 fast enough and that the derivative is small enough here, so that when I multiply by psi and take the derivative, the slope here is not too big. So let's estimate the first eigenvalue. So lemma, lambda 1 times secant square L is less than mu. And the proof, we're going to do a lot of comparison theorem. The proof is very simple. Suppose not. Suppose that lambda 1 secant square minus mu is O. I have a wrong sign over here. It's greater, so it's a greater here. So suppose not, then it's less or equal than 0. Then for all phi, you're going to have that lambda 1 secant phi square minus mu is less or equal than lambda 1 secant L square minus mu, which is less or equal than 0. So this coefficient is less or equal than 0. That means that the second derivative is going to be greater or equal than 0. But you can't have a function that is 0 at one side with 0 at the side and the second derivative being non-negative for the whole thing, unless it's 0. But the first eigenfunction is not identically 0. So hopefully I have the right side over here. So yeah, that's what we prove. And I get confused about secant. I usually rewrite everything in cosine. So I will write some of the inequalities twice. Now, next is a bound from above. This says for every eta in 0L, there exists a mu2, so that mu greater than mu2 implies lambda 1 secant eta square less or equal than mu, lambda 1, same thing, but with cosine on the other side. So it can't be away from cosine L square mu as mu goes to infinity, because if it is, this says that if I take a bound that's here, cosine L squared that's greater, then lambda 1 eventually goes lower than cosine eta square mu. So let's look at the proof. So suppose there is an eta, so that in 0L and a sequence mu k going to infinity, so that you have the opposite inequality. Okay. Then when you look at phi between eta plus epsilon and L, so closer to the borders, then lambda 1 secant phi square minus mu k is greater than lambda 1 secant phi square, same term, and here minus secant eta square. Okay. So I just replace mu k or minus mu k. So put mu k on this side, put this guy on that side, and you get secant eta square. What you see is that this is a fixed positive constant. And in the first equation here, we know that if mu goes to infinity, lambda 1 goes to infinity. So this will go to infinity as lambda 1 goes to infinity. That means that your second derivative goes to minus infinity. And I say contradicts boundary conditions. So if I start, let's say at minus L, then the second derivative of h is so small, meaning minus something so large, that it just goes up a little bit and has to nosedive back down to the x-axis. So there is no way that it's the first eigenfunction. What this gives us is that lambda 1 over mu decreases to cosine L square as mu goes to infinity. Okay. Every time I try a cosine eta square, which is slightly bigger, I can have a mu large enough so that it's less than cosine eta square. So it goes down to cosine L square. It's strictly bigger, but it decreases. And this, actually this, my co-author might disagree. This I found was the key estimate that sort of told us we can finish the proof. So what does it give us? If you look at, again, this equation, you have inflection points where, well, because h is positive, where this lambda secant square minus mu equals 0. So we have inflection point when secant square equals mu equal over lambda 1. And again, the same equality with cosine because I get confused. So inflection points are, let's say, here and here. But when mu goes to infinity, lambda 1 over mu decreases to cosine L square. So when mu goes to infinity, phi star has to go to L. So that's the first part of what I claim would prove. The bound on the eigenvalue gives us that the peaks move towards minus L and L. And yes, I know that the second derivative is positive here and negative here, and there's only 2 inflection points because this function is very well known. Okay, in fact, now we have estimates on the first eigenfunction. So because h is even, it satisfies first h1 prime at 0 is 0. And so we're going to fix phi naught anywhere between 0 and L over 2. The only reason for L over 2 is convenient to double it here. And with bound on lambda 1, we can use a approximate external comparison for the Jacobi equations to get, for this equation, to get that h1 phi between minus phi naught and phi naught behaves like hyperbolic cosine with these coefficients. Well, it makes sense because the second derivative around here is some sort of positive functions or number. We're going to compare it with positive numbers times h, and that's exponential. And a symmetric even function that's exponential is hyperbolic cosine. So it's h1, and it behaves 0 times a hyperbolic cosine. And it's really large because there's a square root of mu here, and then there's a square root of mu times something smaller, but still square root of mu. So remember, I'll show it again later, the Rayleigh quotient, the denominator is this integral. And so we normalize this to be 1. And when you normalize that to be 1, you can prove independently of this first lemma that the integral of h1 square secant square goes to 0 in this little patch in the center here. So when we combine these two, we know that the integral goes to 0 and the function behaves like hyperbolic cosine. The only way it can do it is that if h1 of 0 goes to 0, it even gives a rate at which it goes to 0. So it goes h1 0 square decreases exponentially as exponential of minus square root of mu. And then given the exponential decay, you go back and look at integral estimate, but now between minus phi 1 and phi 1, and we have these estimates. So we can estimate h1 prime square, it's going to go to 0, and we can estimate h1 square times mu square. This is because we're going to multiply by the derivative of psi, our odd function, and the slope of psi is about mu. It's very large. And let's go back to Rayleigh quotient. So with the Rayleigh quotient, we are looking at the Rayleigh quotient of psi h1, where again, this is psi and phi 1 is of order 1 over mu. So this slope is of order mu. And this is standard trick of splitting it into parts. And so the first one, it's not going to be bad. We have good integral estimates of h1 on this tiny interval. You can see that b is the worst one, but this is about mu square when you take derivative of psi times h1. And so we have estimates on that. This is not so bad because it's order mu and not mu square. And this one is just sometimes times a. That's how you prove that the fundamental gap goes to 0. So since the fundamental gap is less than the difference of the Rayleigh quotient, the fundamental gap goes to 0 as mu goes to infinity. So I call this strangling, and I'm going to explain this. So if you look at the domains in the half-plane model, they look like this. If you look at the domain in the Poincaré model, and you draw two geodesics, so RQ and SP are geodesics, it looks like this. That means that actually TU, if you sit down and compute the distance, and there's a nice formula on Wikipedia for distance in of 2 points in half-plane model, the distance from UT is smaller than the distance from P and Q. And there is a neck. So as mu goes to infinity, the neck gets smaller and smaller and smaller, which is the reason why the fundamental gap goes to 0. So in Rn, if I have two balls, and if they're disconnected, then the fundamental gap is 0, because you can put h1 on one side, h1 on the other side, and that's your first eigenfunction. The second eigenfunction would be h1 on one side and minus h1 on the other side, but it's the same eigenvalue, so the fundamental gap is 0. To approach that model with the two balls in Rn, you can put a little tiny neck to connect the two balls. And if the neck is small, the fundamental gap is going to be small. Here, there are necks in convex domains in Hn. So the fact that the neck goes to 0 really tells you why the fundamental gap goes to 0. I am almost done. So a few open problems that now have questions. So what about more strongly convex domain in Hn? What about domains that quote unquote don't have necks? So we have to define what we mean by more strongly convex, so a stronger notion of convexity, one of which is horoconvex, which means that instead of requiring that geodesics connecting 2 points stay in the domain, you require that horosphere or horo curve connecting 2 points stay in the domain. Maybe there's a lower bound. Maybe if we do extra convexity and a bound on diameter, there's a lower bound. Convex domain in CPN, I don't know. People have talked about this. I don't know much about CPN. I've never worked on CPN, but again, I've never worked on HN before this. And what about P Laplacian for convex domain? That's it. This is all I have for today.
Thank you.
Thank you very much, Hien. There is time for questions.
Yes, there's definitely time for questions.
So, Hien, I thought that we also have the bound on Sn, the lower bound reached when you get to the degenerate case. I mean, the degenerate case tends to 3 pi squared over d squared when you get the domain on the sphere to degenerate to geodesic arc. So I thought it's done in one of the papers, but I'm not sure. You said it's not.
I don't know. I haven't looked. So Guofang and other people have looked at what they call lune, like so geodesic from one to the other and from one to the other. And also the question, but those have diameter pi over 2, right? So they have a results for those, and they have results for triangles in on the sphere. There's no result for like geodesic, like little
no. That's what I was saying is that when you have a convex domain that degenerates to just like a segment.
I see.
Which is a geodesic segment.
Yes.
Yeah,
I don't know.
I thought it's the same, but then so maybe I'm wrong.
It's possible that the paper on the lune have 3 pi square over d square as a degenerate. I haven't really looked at that. But I know that I haven't seen anything for, let's say, diameter different than pi over 2 also. So that would give you diameter pi over 2, but I haven't seen anything for different diameters. Because you can't really, it's very hard to compute the fundamental gap of domains in S2.
But it's completely solved on Sn or in general, right? The problem is completely solved.
Is it?
Yeah, I think that there are 3 papers and Guofang participated in 2.
Yes, but they don't have a limiting case.
Okay.
They don't have a limiting case, and they might have one for diameter pi over 2, but they don't have limiting case for general diameters.
Yeah.
So
I think that initially how it started was that the eigenvalue problem for the sphere was only formulated for convex domains that were in one hemisphere.
Yes.
So the diameter was pi over 2, less than pi over 2.
Yes, and I think she told us, like, at least last year, she's like, I don't have any limiting examples. And so yeah, they can compute lunes, but that's what they can compute.
I have a question. So what's Joseph Poltavovich speaking? What about extensions to variable curvature?
Yeah, so Hien, go ahead.
We haven't done it. I suspect that if you can, if you can build a neck, so if at some point the curvature is bounded away from 0 and negative, then
Yeah, so my,
I'm assuming symmetries, and at some point, if you can build a neck and have something symmetric, then it's going to go to 0.
right. So my impression is that probably by methods of comparison geometry, for instance, you should be able to get a similar result in any negatively curved space with curvatures bounded away from 0.
Yeah, but I'm not there. Yeah.
We started to think a little bit about this for warped spaces. So negative curvature, in fact, pinch curvature between two constants, just because it helps with the comparison of the eigenvalues. But we're not, we don't have definite results. It seems it's working similarly, but it's because you see what is interesting here, and actually interesting, what was really useful and easy to work with was the separation of variables, right?
Of course, no,
so
I
that's why.
understand
So
that
that's why.
it's easier. Sure,
Exactly.
Yes.
So we're trying to replicate this in some non-constant curvature, negative non-constant curvature case. But there are a few things that are not exactly the same, because you assume a general metric, right? And the curvature is a minus. Actually, even like we looked, so if you look at warped metrics, you have that the curvature is minus f double prime over f, where f is in the radial function. It's a radial function. So so you still, I mean, the cinch in the hyperbolic works wonderful. The sin in the sign in on the sphere works wonderful. So in fact, what happened in both the Euclidean case and the spherical case is that there is a lot of comparison with there is a comparison geometry, basically because you're comparing the eigenfunctions being log concave, you compare with the model space. So in the negative case, we don't actually have this log concavity. So there is not a good comparison base to start with. So that's one thing. The way I see the difficulty is.
I see.
Yeah.
Okay, thanks.
But maybe you can rewrite things in terms of Rayleigh quotients, and then Rayleigh quotients would be somehow nicer to generalize in some sense, no?
Well, we're trying to use the Rayleigh quotients as much as we can, but it's still a work in progress.
And I had another question. So I think there were papers by Luc Hilaire and Chris Judge who looked at hyperbolic triangles that were sort of getting thinner and thinner and collapsing to a segment. And I think they were trying to say that spectrum of a hyperbolic triangle is simple or something like that.
Who was the author?
I think Luc Hilaire and Chris.
I see. Okay. Now we don't know this.
I was just wondering. I think they were so they had to look very carefully at asymptotics of not just the first two eigenvalues, but of many eigenvalues as a triangle was collapsing to like a segment in a hyperbolic plane, right? And so I was wondering if maybe given what they have done, you could just look and see what happens for triangles, like with a cap and so on. Perhaps it could be possible to track the first two eigenvalues in their example.
I found the paper. Yeah, it's very, very good. You pointed out to.
Yeah, if you can send it to me. Yeah, that sounds very interesting.
So and then I guess there may be similar conjectures about higher eigenvalue gaps, right? I mean, well, I don't know, either lambda 3 minus lambda 1 or lambda 3 minus lambda 2 or something, but.
But do we know about the multiplicity? I'm not sure we know when.
I don't know. I haven't thought about these things, but yeah.
Yeah. We also looked at this case with the horospheres, right? But it's not yet completely solved either. I mean, we don't have a definite result, but it's something interesting happening there as well, right? There is some dichotomy with small balls and large balls. But
and do you know? So there are some nice metrics, let's say on three-dimensional Heisenberg group or three-dimensional solvable group.
Yeah. Okay.
For example, I don't know, Carolyn Gordon and many of her students, these are kind of nice examples. So maybe you could look at symmetric domains in, on those manifolds as well. And you could somehow, by cleverly choosing the directions in which you take your product, or you could take some kind of parallelepiped in those things, and then things would work out nicely for this kind of problem. So, for example, when at some point we had to find examples for negative scalar curvature, and so some examples that were not hyperbolic, we used these things, but so at least a lot of for domains in these manifolds, I'm not sure how much was done, but at least lots of curvatures and stuff were computed before. So, so this is another kind of symmetric example, maybe not as a spherical form, not completely isotropic, but still reasonably nice.
Yeah. Okay, that's a good idea. Absolutely. We'll look for the papers.
Yeah.
I can send you at least the basic. I mostly know the stuff, on a closed manifold, not on a domain in these spaces. But it's you can write things down, I think, in those examples at least. So maybe you could, yeah. I don't know.
Okay.
And but for like Euclidean space, what is known about, I don't know, lambda k minus lambda 1, like lambda 3 minus lambda 1, or like for some k, probably you should be able at least to improve something compared to the lambda 2 minus lambda 1.
Well, there are some universal inequalities in principle, but note that for higher eigenvalues, you may get multiplicities, right? And so it becomes more tricky.
On a surface, multiplicity should be bounded above, right? I mean, there should
be but it's, I mean, as I said, so there are questions of this kind. So people are estimating lambda n minus lambda 1 and lambda n divided by lambda 1. But a very specific feature of this fundamental gap problem is that you know that there is a gap, right? So that lambda 1 is,
exactly.
lambda 1 is simple, and therefore the question is certainly meaningful. So for higher eigenvalues, you don't have that.
And also, so another thing which kind of looked, so I'm not sure, if you look at the first, when you were looking at the drawing the first eigenfunction in this cross section, it looked like it was sort of all the mass was moving to the boundary in some sense.
Yes.
So, and some people in the audience like very much the Stiklov problems, and Stiklov problems. Generally, I think my intuition is kind of a limiting case when you move your thing to the boundary. So, but
Stiklov is a limiting case of the Neumann problem, not of the.
Okay, life is hard, but
it's different.
But can you get some sort of I guess you had some estimates, but can you rescale the eigenfunctions to have some sort of nice asymptotic for the eigenfunctions in the case when things kind of approach each other? some
What do you want to approach, the domain, the eigenfunctions, or the domains, or the?
Yeah, so as the domain gets narrower and narrower, right?
Mhm.
So in your when you do your counterexample, can you see? Can you have some sort of good asymptotics for the first eigenfunction? But it's
Mhm.
once you understand the eigenvalues very well, one can also ask, okay, so what happens to the second or whichever eigenfunction? So. And well, I'm not sure how interesting.
Hien, I think you did some calculations for some, well, for the balls in the hyperbolic, you did some calculations to see how the asymptotic goes when the radius is moving either to 0 or to infinity, and you got some asymptotic. But for other domains, I think, well, there are some estimates, but they're not quite of this type. They're not of so that will be to say how they approach so how lambda2 approaches lambda1 in terms of the epsilon going to, or the neck going to 0 or something, or at what rate, or we actually didn't look at that in that.
No, and we had that it's exponential, right? And so we just pick mu square in that in this integral, but it can probably be much better than mu square. I think I prove it that's true for every single power because we have this exponential decay. So yeah, the asymptotic for ball.
No, but this is just at the neck, right? But is this all that matters? Is how you do it at the neck?
Yes.
Yeah. Okay.
All that matters is how you do it at the neck.
Okay. Well.
Okay.
Yeah, for balls, so that's something I guess Alina can tell you once we publish it and or put it on archive in a month or two. For balls, the asymptotic of the fundamental gap is about 1 over r cubed when r goes to infinity. So it's not 1 over r squared, it goes to 0, like it's 1 over r cubed, let's say. Can't prove it yet.
You can prove it, right? I think you do have, no?
No, we don't have our. I don't remember.
Yeah, well, I saw that this is exactly what. Well, okay, we'll talk because I mean, what is known was something of the order r squared, right? And then that was not good enough to deduce anything about the.
Or maybe we have r cubed, but we don't have a lower bound as r goes to.
We don't. Okay, except when n is greater than 3, strictly greater than 3. No. No. No, maybe okay, maybe not. Okay. All right. Well, okay, it's work in progress. A lot of work in progress.
A lot of work in progress on this.
I mean, you guys know. I mean, I'm totally new at this eigenvalue problem, so I'm counting a lot on my.
No, but we're very happy that you're doing it now.
Yeah. We can talk more now.
Stuff, so, yeah.
Exactly.
Yeah, no,
Yes.
I guess the question is, so once the diameter, if the diameter is not working, can you replace diameter by some other function? Which
Yeah. Maybe maybe this minimal width thing, this I don't know, but then
the length, the bar, the area enclosed. Yes.
Yeah. Okay.
Yeah.
All right.
Area will not help in the hyperbolic, but
no,
something else. Okay.
But so yeah, I am new also to this eigenvalue thing. I have done gluing constructions up to now, but this was fun.
All right. So, if are there any other questions? Well, if not, I would like to thank Hien once again for a great talk.
Thank
you.
And So next week there will be another talk about the first eigenvalue, but this time for differential forms for the curl in 3 dimensions. So maybe some. I hope you could make it. All right. So thank you very much for coming,
Thank
and
you.
have a good weekend.
Thank you.
Thank you for the nice talk.
Very much.
Thanks.
Thanks.